Okay, I think it's visible now, right?
Yes.
Okay. Okay, so this is the first technical session. I'll keep my notebook handy. If you have any questions and I don't know how to answer it, we'll keep a note of it. So let's start with the meaning of the word geometry. So how many of you know the meaning of the word geometry already? So is there anybody who knew that the meaning of geometry is what I am showing here? All right.
Yeah.
Okay, great. Somebody knew. That's good to know. So the meaning of the word geometry is the measurement of the earth. I think I can take a pointer here. Right. So my pointer is visible, right?
Yes.
So the word geometry originates from the ancient Greek word geometria, which has two parts to it, geo and metria. Geo means earth and metria means measurement. So therefore, the literal meaning of the word geometry in Greek is the measurement of the earth. And I'm showing a picture here. It's a nice picture. It's an artist's illustration of something happening somewhere in Alexandria. Anybody has a clue what this picture is about? So there is a person, he has some tools. He's looking at the sun and there's a globe. So this is Eratosthenes. This is 300 BC, about 300 BC. And this is Eratosthenes. And this gentleman, he was a librarian and he measured the perimeter of Earth more or less accurately by looking at the sun. So what he did is he looked at the sun from two different places and measured the elevation of the rays and then more or less accurately calculated the perimeter of the Earth. So it's a nice thing to know. Even otherwise, like measuring the Earth, like when you were in high school, there were questions like you have a polygon and the polygon is representing a piece of land. You want to fence that land, and there is some cost of fencing per meter, and then you have to sort of tell how much is the cost of fencing that land. So a lot of questions which are related to measuring the land, in fact, arise naturally in geometry. The other thing that arises naturally in geometry are the shapes. So squares, triangles, circles, pentagons, parallelograms, these charts, these are 2D shapes that we can think of. And then there are spheres, parallelepipeds, many 3D shapes as well, cubes, right? So right from the moment you get up in the morning, you hold your toothbrush, you drink water from a bottle. Right now you're looking at your phone or I'm looking at my laptop. All these objects have geometric shapes. So I'm sitting on this chair, which is on this floor, which has tiling, which are geometric shapes. So if nothing else, the presence of so many geometric shapes around us should be sufficient to motivate us to work on geometry, think about geometry, discuss geometry. I think it's enough motivation. But that said, let's look at something that we have seen already. So this is the problem from high school. Like you must have seen this kind of problem in your high school, and these kind of problems are part of Euclidean geometry. So here you can see an isosceles triangle where the size of the equal sides, I mean the length of the equal sides is A, and the angle between the two equal sides is theta. And the quantity to be computed is the perimeter of the triangle. So what needs to be done is to measure the length of the base of the triangle. And I believe that all of you have seen such questions in your high school. So you can observe that you can drop perpendicular to the base and then do some computations and then find the length of the third side. The other thing you can do is you can apply cosine rule and conclude that the length is square root a square plus a square minus 2a cos theta. And all these things, like I think this is already familiar territory for you. So another branch of geometry which I think we are familiar with is the coordinate geometry. So to recap, in coordinate geometry, we can represent geometric objects with some equations, some algebraic equations. So for example, in this figure, we are denoting 2 points by a pair of numbers called coordinates. So x coordinate followed by y coordinate. And the question we're asking is that what is the equation of the line passing through these 2 points? Right? So you know how to do these things, how to handle these things. This you have seen in your high school, but this is not all of geometry. Geometry is a humongous subject. Geometry is much larger, much bigger thing than what we have seen in high school. So here I have listed a couple of branches of geometry. So the one we're most familiar with, the Euclidean geometry. Then comes the non-Euclidean geometry, hyperbolic geometry, elliptic geometry, many other things which I myself do not understand. And the other familiar domain branch of geometry is the coordinate geometry, which is also called analytic geometry. Then there is differential geometry, topology, algebraic geometry, discrete geometry. So discrete geometry is also called combinatorial geometry. And then there is computational geometry, convex geometry, projective geometry. So in this workshop, we are going to know one more branch of geometry beyond high school, that is computational geometry. So in fact, I think in many undergrad colleges in India, the course computational geometry or geometric algorithms is not offered. So I would say that this is also beyond undergrad course in some sense. Okay. So far so good. Any questions? So I'm getting some mails that some people are not able to log in. It is very unfortunate that I cannot fix this now. So I would request you to log in like 4 or 5 minutes before 5 o'clock so that face problems. So let's move ahead. All right, okay, so what are we looking at? So we are going to look at a branch of geometry called computational geometry. And to give you a flavor of what computational geometry is, we will start with the concrete problem. So here in this figure, you can see a bunch of points. And these points are sort of placed in certain fashions, some continuation. Do you see what is the pattern in these points? These points are all lying on a horizontal line, right? So let us say there's a line on the x-axis. And so therefore the y coordinates are all 0. And I am showing only the x coordinates. So this is at 4, 0, this is at 8, 0, this is at 17, 0, 34, 0, 36, 0, and 52, 0. So many points. And the concrete question to ask is to find those 2 points that realize the closest distance, the smallest distance. So we want to find 2 points which are closest to each other. So this is a proximity question. So which 2 points are closest to each other in this figure? Okay, Rutvik is saying 34 and 36. That is correct. So how do you know that these two are the closest? Like, what is the proof that these two are closest, like, or how do we arrive at this conclusion that these two are closest? Compare the differences. Compare the differences of what?
Like comparing the value of the numbers.
Right. So what are you comparing? Are you comparing 4 with 17? Or are you
Yeah,
only
you
comparing?
do it for all and then decide which has the lowest value.
Correct. So basically here you have how many points? Here you have 6 points, and you have to compare every point with every other point. So for every point, there are 5 comparisons to be made. So there are 6 points. So 6 into 5, 30 comparisons will be required, and then you will be able to claim correctly that 34 and 36 are closest. That's perfectly fine. So the question is that instead of a couple of points, if you're given a set of n points on the horizontal line, then how will you find the closest pair? Similar thing will work. Similar thing should work. Only that now the number of comparisons will be in terms of n, isn't it? So can you tell me, in terms of n, how many comparisons will be required to find the closest pair of points when you are given a set of n points?
N into n minus 1.
N into n minus 1. Who is that? Ritvik. So another thing to notice is that when you compare, let us say here in this picture, when you compared 4 to 17, there is no need to compare 17 to 4 once again. So first you start with 4. You compared 4 to 8. Fine. Then you compared 4 to 17. You compared 4 to 34, 4 to 36, and then 4 to 52. Then you come to 8. There is no reason for you to compare 8 back to 4 again, right? So certain computations, certain comparisons can be avoided.
NC2.
Right. So somebody said n choose 2. So what is n choose 2? N choose 2 is n into n minus 1 divided by 2. So that means the previous answer we had n into n minus 1. I'm not able to write here. In fact, I'm going to move to whiteboard soon. But listen to me. Try to hear me out. So naively, if you think there are n into n minus 1 comparisons, but half of the comparisons can be avoided. Because for every pair, for example, 8 and 34, if you have already compared 8 to 34, you know the distance between 8 to 34, that is 34 minus 8. Then you do not need to compare 34 again with 8. So half of the comparisons can be avoided, isn't it? Okay, so the number of comparisons comes down from n into n minus 1 to n into n minus 1 divided by 2, which is nothing but n choose 2. All right. So now, yeah, so our output, so what do you want to output? So arc mean is what? So this is a symbol. If you don't understand this symbol, don't worry about it. The point is, we want to find that pair, point I and point J, whose distance is minimum. That's what I mean. So the question is, what is the running time? So the running time is going to be the number of comparisons we have made. Because to make one comparison, that is to compute the distance between, let us say, 17 and 36, we have to perform one subtraction. That is, we'll subtract the smaller number from the larger number, and then we'll get the distance. Is that right? So far, so good. Every comparison requires computing the distance between two pair of points. And therefore, since the number of pairs is n choose 2, the running time is also order n squared. So is there anybody who does not understand this capital O n squared notation? Then I will talk about it. one person does not listen. So point is, n choose 2 is like n into n minus 1 by 2. Okay? So I can say that it is more or less like n squared. So it is called asymptotic notation. So that means if you have a function in n, and the function could be complicated. So for example, here there are two terms. There is a term n squared by 2, and then so what is n into n minus 1 by 2? N squared by 2 minus n by 2. Okay, so there is a term which is in n squared, and there is another term which is in n. But the larger order term, so these are two monomials. So n squared by 2 has degree 2, and n by 2 has degree 1. So the larger order term always dominates. So we say that, okay, n choose 2 is sort of like order n squared. So I am being only semi-formal here. So there's a formal definition of the big O notation, which we will talk about maybe when we move to this whiteboard. So this notation means that overall, somewhat like n squared comparisons are necessary. So believe me for now. So this is a way to understand the big O notation. We'll look at the formal definitions slightly later. So the question is the problem solved? So we have definitely found the correct solution. We know for a fact that we have this algorithm that compares every point to every other point and computes the pairwise distances and then outputs the pair of points that realizes the minimum distance. So correctness is not a problem. So as far as correctness is concerned, we have found the 2 points which are closest to each other. But have we found the solution quickly enough, or is it possible to sort of make less comparisons? Is it possible to bring down the running time further from something like order n squared to below? Okay. So is there anybody who has any clue that how one can find the closest pair of points in better than n into n minus 1 by 2 time?
Sort them and compare pairwise adjacent ones.
Yes, who is that? Yeah, please, can you tell your name so that I can.
Suhas.
Suhas or Subhash?
Suhas.
Suhas, right? Suhas, good. Yeah, this is a better technique, right? So if you sort the points, so what is the running time of sorting n numbers?
If you use some better sorting techniques, it will be around n log n.
That is correct. That is correct. So in n log n time, maybe using mark sort, you can do in n log n time, you know that what is the ordering of the points from left to right. And then what you do is you do a pass from left to right. So you know for a fact that if at all in the closest pair 4 has to appear, then 4 has to appear with 8 because 8 is the closest to 4. Now let's look at 17. So you know for a fact that if 17 has to be reported as one of the points in the closest pair, then 17 would be reported along with 34 or with 18, the neighbors only, the neighbor to the left or the neighbor to the right, nothing beyond. Because you know for a fact that the distance between the neighbor of 17 to the left, that is 8 and 17, is smaller than the distance between 4 and 17. You have this observation. So there is no reason for you to compare everything else with 17. Does it make sense?
Yes.
Anybody? Anybody who doesn't understand, who thinks that there is an issue?
Sir, what you're saying is basically we should take pairs which are adjacent to each other and keep on going and see which is the smallest, is it?
Yes, once you know the ordering, that's what you should do.
Okay, okay.
So what is the definition? So somebody, Vidush is saying that dividing the space based on how we define nearest. Vidushi has said something which makes sense. So yeah, more or less correct. So she's saying dividing the space based on how we define nearest. This is more or less what we have done, right? So once you know that this is the increasing order of points, you know that 4 is followed by 8. The next point to consider is 17. And the next point to consider is 34, 36, 52, and so on. Then you do a pass. You check what is the distance between 4 and 8. So you know that is 4. So right now you believe that, okay, maybe 4 and 8 are the closest, but their distance is 4. Then you compare 8 to 17. Their distance is already 9. So you know that it is not a candidate pair to be the closest pair. Then you compare 17 to 34. Again, it's not a candidate pair. It's very far apart. Then you compare 34 to 36 and you realize that the distance is only 2. So now your initial guess of the closest distance was 4. And now you realize there is a better candidate. There's a pair of points closer which have only 2 distance between them. So then you update your closest pair from 4,8 to 34,36. And then you check the distance between 36 and 52, and you realize that these two are far apart. Then you are ready to conclude that 34,36 is the closest pair. Okay, so
Sir,
yeah, go ahead.
sir, in this diagram, it already seems like it's on a number line, so we can avoid sorting, no? So you are basically talking about a set of numbers, probably.
I'm
Then we
basically
have to sort.
talking, yes, I have given you an array. Suppose you are writing a program. I have given you an array, but I have not said that the array is already sorted.
Ah, okay, sir.
From the figure, you can tell just by looking at it. That is the beauty of human intelligence. No computation required. Okay. So far so good. You realize that n log n time is the time to sort, and you can do that in n log n time. But can you do even better? Can even less time you can do? Can you capitalize on this observation that for every point you just need to check the neighbors. So if you sort, then you have already lost the game, because as soon as you sort, you incur n log n time. That is the lower bound. Lower bound means the minimum time required to sort n numbers deterministically is n log. That is no. So if you sort, you already lose the game. My question is, can we do it in better than n log n time? So let's be more specific. Can we do it in order n time? Means some constant times n time without sorting. Of course, if you sort, you are done. I mean, you have lost. So you give it a thought for a minute. Oh, so somebody is asking, will binary search help here? So the point is, you see, if you can do binary search only when you have sorted the points. So you have been given an array of numbers. You do not know whether they're sorted. So you are sorting. Then you are applying binary search, right? So n log n time is already lost. Do you see that? Okay, so now Now we'll check. So you have an understanding of what is a computational geometry problem. And so this is geometric algorithms workshop. An algorithm that solves a computational geometry problem is a geometric algorithm, more or less. Okay. So you have seen that, okay, this is a candidate computational geometry problem, and this is how one can approach it. So we have seen an n-log n algorithm for it. We do not know whether order n algorithm is possible. Right now we don't. So now we'll say that a problem is solved when you have a correct solution and when we have sufficient confidence that the solution that we have found did not take much time. I mean, it has been found quickly. So now we'll change gears. Now I will start sharing my tablet so that I can write on it. What's necessary to write? I'll be able to write on the tablet. Okay, here's the share screen option. Share screen, start broadcast. Okay, so I hope you can see my screen.
Yes.
So now we'll move one step forward. Now you are given two arrays. Let's call the next symbol. So you have two arrays. You have seen what is an array. They contain some numbers. The two arrays are of equal size. So the number of elements in X is equal to the number of elements in Y. So now, what do these numbers signify? So this is, let's say the indexing starts from 1. So 1, 2, 3, so on. Let us say there are n numbers. So X of 1, comma, Y of 1 signifies the coordinate of a point on the plane. All right. So basically you have been given n points on the plane and the representation is via numbers. So let me draw how the points are. So let us say the points are sort of, you look at these two arrays and you open your favorite editor and draw the points. Or you can also open your notebook and draw the points. So you have seen that, okay, these are the points that I have. Again, I ask the same question, that find the closest pair of points. So what shall we do now? You understand the question? Is there anybody who has a doubt on the question? Please feel free to ask me, because not understanding the question means that you won't follow me further. So I'll repeat the question once again. So you have been given n points, and these points are represented as pairs of numbers. Your objective is to report, let us say the first point is P1 and the last point is Pn, the ith point is Pi. So you want to output that pair of number. I'm not going to use notation for simplicity. So I'll just write in words. So you want to say that, okay, I have two numbers pi and pj, and I know for a fact that the distance of pi and pj is the smallest among all pairs. And then you have to justify that. How do you know this? Then you have to tell me what is the algorithm. So in this figure, it looks as if that these 2 points are nearest to each other. This is the closest pair. So any clue, any idea, like what should be the first step? Can we just think of this also in the 1D terms? Is it possible to somehow convert this problem into the 1D version that we have already seen? The one-dimensional problem was simpler, right? There was a line. And within the line, we could sort. Now, the idea of sort will not help. If we sort, shall we sort in the x direction or shall we sort in the y direction? And what do we do next? All sorts of confusions will come. You understand the problem with. So let us try to do it. So if we do the following, if I suggest the following, that if you project, so what is projection? So let us say this is the x-axis, and I'm dropping one perpendicular to the x-axis from every point. So Ritvik is telling you will have to subtract the vectors and optimize on the distance right. Oh, okay. So you're saying that why don't you look at them as vectors? Okay, so that's a good idea. So if you look at vectors, so if you think that, so the problem is if you compare every point, so if this point is a vector, this point is another vector, you compare them, even y is vector equity, you can simply find the distance between the two. Simply find the distance. So like previously, to take this point, find the distance of this point with everything else. That is n-1 time. Again, this point n-1 time, but then you can avoid duplication. So n choose 2 time is always sufficient. You know for a fact that you are not going to take more than n into n-1 by 2 time. But the question is, can we do better than this? So our what we call brute force approach. So this comparing everything with everything is called the brute force approach. So brute force will always work. Correctness is not a problem. The problem is running time. It is not going to be fast. It is going to take n into n-1 by 2 time. So we want to avoid so much time. So you say that, Ritvik. All right. So Ritvik agrees to that. So now what can we really do to sort of get down to order n squared to order n log?
So can we project on x-axis and also project them on y-axis and then just see which is the absolute value, like sum the absolute values of the differences in points or something like that. I don't know.
Correct.
Because both has
Yeah.
to be like minimum something.
Wow. This is a good
And I was thinking
observation.
the same thing. You take the difference, like you do the same linear sorry, what am I telling? N log n search that you did for the points on a line, right?
Yes.
You do that, but you do it twice, once on the x-axis and once on the y-axis.
Mhm.
And then you take the square root of the sum of squares of both of them and try to find which has the minimum value there.
Well, I understand the approach that you have suggested. Both of you have suggested. But then the thing is, we have to be doubly sure that we have not made any mistakes. So let's take a simpler example. So you understand the question.
So I was thinking, can we treat it as a traveling problem? Like, can we connect all these points and treat it like a simple graph travel algorithm or something like that, which we already might have? Would that approach work in this scenario?
Can you be more specific? What do you mean by traveling approach? So you have these
Like
points.
Yeah, like we know about this disastrous algorithm or DFS, BFS. Can we
Okay.
treat? Yeah, like
So you want
that.
to make a graph. So I understand. So you're saying that why don't you treat these points as vertices of a graph,
Yeah,
and
and
then
we the shortest path, and in that shortest path, we'll always. I mean, we'll have the minimum distance in that shortest path only.
so if I understood what you said that treat these points as vertices of graphs.
Yeah.
And then you have to define the graph by defining what are the edges.
Yeah. What are the edges? So, I mean, we have to look at some weight, and I mean, the weight can be the distance, something like that.
Okay. So you're saying that for every pair of vertices, you're going to add an edge, and you will set the weight of the edge as the distance between the two.
Yeah, that might work. And we will take only the minimum distances that can connect the graph and make it a tree or some structure like that. But it will have to be compared with every point. So I think it will be costly in computation if we go.
Yeah. So we want to avoid comparing everything with everything. We don't want to choose two kind of thing. We want to do some
Yeah,
sorting kind of business.
yeah, I get it. Yeah.
But thank you for the suggestion.
Yeah,
Because
absolutely. But
what happens when the department will discuss, when we discuss, new things come up. Like I had a slide where I said there was a nice quote that alone we can do so little, but together we can do so much. I
yeah,
really like it.
absolutely. Thank you.
Yeah. So there's some conversation going on. Naren is saying that you won't get the same pairs of neighbors when you do the two axis thing. Makes sense. Makes sense. So for example, if you drop this P1, so let us say I call it P1. So Naren has made a good point. So I call this thing as P2. So this point I call it P1. This point I call it P2. And now he's saying that if you drop P1 to and P2 on the x-axis, you see that there is no other point projected between P1 and P2. So these two are neighbors. But on the other hand, if you let's call this next point as P3. If you project on the other side, on the y-axis as well, then what happens is P1 becomes neighbor to P3. Whereas in the other case, P1 and P2 are neighbors. So even to decide whether P1 and P2 are nearer or P1 and P3 are nearer, that is not clear. That's what you're saying, Naren. Okay, so let me show you why this approach will not work. So when we think about algorithms, designing algorithms, we try all sorts of wild ideas. Our mind goes wild. We have so many ideas, so many things we brainstorm, and then we discover that some ideas will not work. So there's a famous saying with Thomas Alva Edison. So he was a great inventor, but he had failed many times in life. So, but he never agreed to that. He said that I have never failed. I only discovered 10,000 ways that do not work. So now we will discover one of the ways that will not work. So which is this approach, projection approach. I'll give you a counter example. I mean, I'll try to do so. I know for a fact that this doesn't work. So here's the x-axis. Here's the y-axis. So I want to draw 2 points which are closest in terms of projection, but very far apart. All right. Again, I want to do the same thing in the y direction also. So let's do the other projections also. We'll call it P3, we'll call it P4. So I can see looking at this configuration that P1 and P3 forms the closest pair. I mean, this is also a good candidate, but let us believe that P1 and P3 are closer than P2 and P3. All right. But if you do the projection, it will make you believe. Oh, so there's a problem. Oh, so, no, there's a problem. So I did not project this, right? So here P1 and P3 are close by even in the x direction. So I have to I can move things around. You understand the problem in this figure? So I wanted to show you a figure where the closest pair of points is not captured either in the x direction or in the y direction. So if you draw projections and you say that, okay, I see that projection wise, these two points are close by, the closest in x direction, and projection wise, these 2 points are close by in the y direction, and you will, let us say, output one of the two with some logic. Then you will fail. That's what I want to prove. So let us move things around. So you see that this is possible. So I can spend some time and draw it that even if you report the better of the two projections, it will still fail. But you get a sense of what I'm saying, why this will fail. So a counterexample can in fact be formed. Do you get a sense of it? Nobody's getting a sense of it. Then I'll draw the counterexample and then we will move forward. Okay, let's draw the counterexample. Since we're not sure whether this approach will work, we have to either summarily reject this approach or we have to say why it works.
Sir, also we can't sort two arrays independently because the one should be correspondent with the other. X and Y should be same. So if we sort separately, we'll go wrong.
No, so you have two arrays to start with. One is the X array, which contains the X coordinates. The Y array contains the Y coordinates. So it is possible to sort the X coordinate separately and also possible the Y coordinate separately. But you were saying that then you will not have sorted the points. That I agree. That by sorting separately, you will definitely not sort the points. That's what you're saying?
Yes, sir.
Yes, absolutely true. But I'm saying that since the points are on 2D, so we do not know, we don't have control over their heights and the X coordinates and Y coordinates. Can we do something by separately sorting X coordinate and Y coordinate? So that's what we tried to do. We tried to project points on the x-axis and then check whether according to projections. So once we have projected, we have a 1D, one-dimensional setup that we have already solved in environment. Then we thought that, okay, can we report the closest pair here or the closest pair here, and that will give us the correct answer. So what you were saying is correct, but this is the approach we are trying to see. And we are trying to reject that approach by showing a counter example. Are we good here? Okay, so let's move some points around. So can you tell me where I should move P1 so that it still is participating in the closest pair, but not in the X direction?
What if you start by like taking one point
Okay,
and well draw a circle around it?
you start
You
with this
know,
point.
yeah. You draw a circle around it and see how many points lie within it. I mean, technically you go from, circle of radius 0 to, well, till whichever point hits it first,
All right, all right.
right? Um, so, and well, that will give you like the distance between those two.
So
So
we will
you,
be able to identify which is the closest point to the given point.
yeah, by doing that to like, yeah, exactly, right? Closest point to that given point. So now you just need to apply that for every point and you'll get which is the closest.
Correct. Makes sense. So that is true. That is a valid approach. So I thought that you were giving a counterexample to this approach. So you have given a new approach. Okay. So I will give you a counterexample to this. Maybe after the break or maybe tomorrow. I am not able to find the counterexample now. But let's look at this other approach that
So
Rutvik has
for the
suggested.
counter example,
Yes.
so for example, we are fixing one X, okay, maybe 1 or 2 something, and the Y one can be 1 and the other Y can be infinity, like it goes on to the top like crazy, it goes up.
Oh, wait. We'll start from the beginning. We will go to Ritvik's approach later. Let's look at the counterexample you're suggesting. So tell me from the beginning, what is the counterexample?
Yeah, so for example, pick a point, pick X as 1 or 1 unit, let's say, and for that point 1 P1, you pick as Y as 1 itself. So 1 is a point as an example.
Okay. This is one.
Now P2 will have the same X coordinate, but the Y will tend to infinity.
Okay, so it's somewhere
But
at
the
the infinity.
projection will, yeah. So the projection will be very close to x or the same x itself. Similarly,
Correct.
you pick a point on y equal to 2 or something.
Y equal to 2. Okay.
Yeah, and x is 1, let's say. And then again, similarly, the x will be infinity for P4. So this is P3 now you're drawing.
So you are taking 1, comma 2.
Yeah, now for the same y, which is 2 here, x will be infinity. So infinity comma 2, let's say, something like that. So the projections are very close to each other, but it is too far as a counterexample.
Oh, wow. Makes sense. All right. All right. So what he's suggesting, let's drop the perpendiculars now to understand. So instead of 1, comma infinity, I will make it slightly more than 1. So I'll make it 1.1, comma infinity. That will also make it keep it close to 1. So I'll say it is 1, comma 1.1,
Yes, sir.
comma infinity.
Yeah, because the projections are extremely close to each other then.
Yes. The other one I'll say infinity, comma 2.1. All right. So now the projections are very close to each other, as you have correctly pointed out. So the gap is only 0.1. That is the gap. And here also the same thing is happening. The gap is only very little. Whereas, what is the closest pair of points? These two. Let's take together. These two have a distance of only 1. This makes sense, isn't it? Does it make sense to everybody? Is there anybody who objects to this?
What was the approach for finding the points? Finding the shortest distance.
So there are 4 points. He has given only 4 points. He is constructing a counterexample. He says that look, take this point 1, comma 1. So input contains only 4 points. So in the array x and y, there are 4 entries only. Is that fine?
Yeah, okay.
So now you know the distance between every pair. So now what you can see is visually we can see that this is the smallest distance. This is the closest pair. But in the projections, if you see, this point and this point are closest in terms of x projection. And this point and this point are closest in terms of y projection. Isn't it?
Can you name the points like P1, P2?
All right. Makes sense. Let's be more precise.
ABCD.
So in X projection, P1 and P2 they lie on the same point, right?
Close by. Oh.
No,
There
it
is a
is 1,
problem.
so they do lie on the same.
Oh, sorry. There is a problem.
Just take P2 as 0.5, comma 2. That's it. The counterexample will still hold.
Yes.
Oh, yeah.
So you have to make some adjustments.
Okay. But the approach is okay. But yeah, thanks for the correction. Also,
Yes.
I'm getting carried away, I think. Okay, anyway. So this is P2, which is 0.5, comma 2. That is the beauty of discussion. I did not plan that I will talk about it today, but since nobody was convinced. Okay, so how do I move this thing? So now, as per the X projection, the closest points are P1 and P4. they have a gap of 0.1 only. As per Y projection, the closest points are P2 and P3. But in reality, the closest pair is P1, P2. Does that make yeah? Is there any objection to this? So Ashwin is saying, shouldn't the fourth point be 2, 2 instead of 1, 2? I don't understand. What is the fourth point, Ashwin? Oh yeah, so Ashwin had also found out this issue. That's what I understand from his message. Oh, one more suggestion was said by Soham. Soham said that imagine a right triangle with perpendicular sides parallel to axis. Then closest pair of points will be in the two axes. Let's look at this. Yes, even simpler thing. So Soham is saying that imagine the right triangle with perpendicular sides parallel to the axis. This is what you're saying. This does not work. So if you project these 3 points on the right triangle, then what will happen is these two will be projected at the same point, distance is 0. And these two will be projected at the same point, distance is 0. So the smaller of these two, so let us say I call it base and I call it perpendicular. So the smaller of B comma P is what will define the closest pair, and that will be captured. I think this is not the correct counterexample. So what do you say? Or did I misunderstand you? Are you there, Soham? All right, fine. So we will believe, I mean, not believe, it's a fact with this counterexample that our approach will not work. Fine. So let's go to the other approach. So I think it's time for a break already. So in 2 minutes or so, we can take a break. And then, so let's do one thing. So here is the other approach that let's first understand the approach. So what he's saying is that, what Rutvik is saying is that look at every point and grow a circle. Keep growing the circle, keep growing the circle, keep growing the circle. At some point, you will hit a point. So that is the closest point from the center. So from P1, you will be able to identify what is the closest point. From P2, again, you're going circles and you will be able to identify what is the closest point. So therefore, from every point, you will know what is the closest point. So you have n candidates. You have n candidate pairs. And out of them, the one pair realizing the smallest distance, you should output. That is what Soham has said. I know, Rutvik has said. Isn't it? Have I understood you correctly?
Yes, sir.
All right. So at this point, I think all of you gave it a thought that what will be the running time of this approach? That what is the running time? To implement this algorithm, what is the running time in terms of n? So we give it a thought for 10 minutes. Then we can come back at 6:30 and we can continue. Is that fine?
Yes.
Okay. So we'll see each other again at 6:30.